Hello everyone, my name is Jinyu. I'm glad to introduce our work to you. This work focuses on designing and implementing a RDMA-based remote fork mechanism that is able to quickly fork OS processes across different machines. We will show its performance benefits for serverless computing. This is a joint work with my colleagues from iPads of Shanghai Jiao Tong University. As shown in prior studies, container startup is slow for short-term workloads like serverless functions. Considering this simple Python program here, its execution actually only needs 2 milliseconds, while if we run it with a Docker command, the total execution time will increase to 18 seconds, leading to 9,000 times overhead. In this work, we propose mitosis, which aims to optimize the container startup. Different from related work, mitosis minimizes the resource usage for boosting the startup and considers a distributed setup. First, it can launch a container within 5 milliseconds on a clean machine with no caching for the containers. Second, it can start more than 100,000 containers on 5 machines in 1 second. Let's begin by analyzing why containers code start is slow. Starting a container to run the application involves many steps. First, it needs to download the container image. Second, it requires the OS to set up C groups and namespaces. Third, the initialization of runtime like Python also takes a substantial cost. We can accelerate each step of the container startup procedure. For example, we can accelerate the image download with a fast network. We can skip creating C group and namespace on the critical path by using a pooling mechanism. As for reducing the runtime initialization overhead, the basic idea is reusing initialized states from other containers. The runtime initialization procedure basically consists of loading the downloaded modules, generating the bytecode, and executing the module init routines, which is actually initializing the container memory. So a new container can inherit the states from another initialized container without downloading the image or initializing the runtime. So the question is how to inherit. The novelty of mitosis resides in how to achieve container inheritance with minimal resource usage. Suppose that we have n containers to start. How many initialized states are needed for the fast boot? The required number of stored states is usually termed as provisioned concurrency. What we want is no provisioned concurrency, which means that the provisioned case is irrelevant to the number of containers to start. So reusing initialized states from another containers to speed up the container startup is already investigated by some existing studies. Let's revisit them first. One such an approach is caching. We can start some containers in advance in order to use warm start instead of cold start. For example, we can create a Docker container first and then use Docker pause to turn it into a cache instance. When there is a container launch request later, we can resume the paused container for the execution. As such, the container construction procedure is skipped. However, if we want another container warm start, we need another post container. Considering the case of pulling up a number of containers together, if we want to minimize the total pulling up time, we have to prepare the corresponding number of cache instances in advance. This means a lot of resource usage, and it requires to explicitly set the number of cached instances for the ideal performance, which is actually hard to determine. Another existing approach is leveraging fork to accelerate the container startup. Fork was originally proposed to speed up creating a new process, and is used by priori work to speed up the construction of a new container. By forking a new container from an existing one, the new container can inherit the initialized memory state from its parent container in a copy-on-write way. An advantage of such a mechanism is in that one parent container can fork many new containers. Nevertheless, what if there is a load spark and we need to launch a number of containers across different machines? The existing forking solution still needs provisioned concurrency. Specifically, we need to deploy one parent container on each machine in order to achieve fast boot. Our system, mitosis, proposes a new OS primitive called remote fork, which is a generalization of fork to remote and enables no provisioned concurrency in a cluster. One remote fork consists of 3 phases. First, a container is initialized as before on one machine. Second, that machine invokes a prepare interface to make the parent container. Then, another machine can invoke a remote fork interface with designating the parent container, which will fork a new container from the remote one. After that, the container workload can directly run. The technical challenge of mitosis is how to implement remote fork efficiently. CRIU is an existing tool that can be used for container or process migration, which can be regarded as one implementation of remote fork. It supports to first checkpoint one process on a machine and then restore it on another machine. Specifically, the checkpoint phase will stop the process and dumps its memory into a file, which can be stored in a distributed file system. Later, the restoration phase will reconstruct the process memory according to the file and resume the process. Although such a solution can reduce the container startup latency when the container memory usage is small, its overhead increases rapidly as the container memory usage increases. There are 2 reasons. First, checkpointing the entire container memory is costly. Second, storing the memory content in a file and transferring it through a DFS is also costly, even though RDMA is used for the network transferring and the file is only in memory. We observe that RDMA network technology actually offers an opportunity to design an efficient remote fork mechanism. As a fast networking feature in modern data centers, RDMA allows direct remote memory access with both high bandwidth and low latency. Thus, a forked child on one machine can use RDMA to directly read its parent's memory on the other machine. Meanwhile, its CPU bypass feature allows us to imitate a local fork, although 2 processes are actually separated on 2 machines. Therefore, mitosis co-designs remote fork with RDMA. A parent machine first starts a container and then turns it into a parent container, which is called a preparation procedure. During this procedure, the memory of the parent container is marked as copy on write. A child machine can then fork a new container from this parent container, which is just like creating a link container but with the parent container's page table. Recall that the goal of remote fork is inheriting the initialized memory states. The child machine will use RPC to read the page table located on the parent. We use RPC here because if one-sided RDMA is used in this step, too many network round trips will be involved. After that, the forked container can continue to execute. During its execution, page faults will happen since the actual memory pages are still in the remote. In the page fault handler, the OS will use RDMA to retrieve remote memory pages on demand, which is similar to the original copy on write. Sorry. Compared to the checkpoint restore-based remote fork, mitosis can eliminate the overhead of both checkpointing and state file transferring, and thus can quickly fork a container from any remote machine. Compared with other state-of-the-art solutions of fast container startup, mitosis makes a better trade-off between performance and provisioned concurrency. Serverless computing is a killer application of our system. It allows users to upload applications as functions. The serverless platforms will automatically deploy the functions in containers and provision the features like auto-scaling and pay-as-you-go. Mitosis can bring two key benefits to serverless computing. First is resource-efficient auto-scaling, and second is fast state transferring between serverless functions. Let's first see the resource-efficient auto-scaling. For elasticity, each serverless function invocation will trigger the start of a new container. After the function execution, the container will be destroyed and the resource will be reclaimed. Typically, the cleanup can be delayed and thus the container can be cached for a short period. During this period, cold start can be prevented, yet here is a trade-off between the resource usage and the performance. Mitosis can achieve high-performance auto-scaling in a more resource-efficient way. Here is a real workload trace from the area function. As shown in the figure, there exist load spikes of concurrent function requests. FN is an open-source serverless platform that caches containers for a short period to avoid cold start. Nevertheless, it may make much memory occupied, as the blue line shows. In contrast, when we integrate mitosis into FN, the memory resource usage is significantly reduced. Meanwhile, mitosis can also reduce the tail latency, as it can always avoid the cold start. This experiment shows that mitosis can save memory thanks to no provisioned concurrency. Remote fork can also speed up the state transfer between functions in serverless workflows. A serverless workflow composes multiple functions into a more complex application. These functions may have dependencies, with one function producing the state that is consumed by the following function. To execute a serverless workflow, a coordinator will start different functions on multiple nodes, as shown in the figure on the right. The current issue with serverless workflows is the slow transfer of states between functions. This is due to the fact that transferring states requires serialization and deserialization, which is a slow and computationally expensive process. Serialization and deserialization is necessary because different functions are isolated with different containers, and their address spaces are different. But what if we bring mitosis to serverless workflows? Specifically, what if we start the consumer functions container by forking the producer's container? Since the transferred data has already been pre-materialized in the parent container, there is no need for serialization and deserialization. In other words, we make state transfer for serverless functions to be optimal, even across nodes. We omit many implementation details in this talk. If you have interest in our paper, please check it. Please refer to it later. In conclusion, we introduced mitosis, a faster remote fork a primitive based on RDMA. It enables no provision concurrency for serverless functions and supports fast state transfer between functions. Our code is available on the GitHub. Thank you for your listening.